Hi. First of all, congratulations for completing the activity. As promised, I'll explain to you the relationship between phocomelia and thalidomide. On October 1, 1957, a new over-the-counter drug was introduced in West Germany. It supposedly cured morning sickness during pregnancy. This drug was called thalidomide. Thousands of women bought the drug and were relieved when morning sickness was gone. Everything looked great until the end of the following year, when thousands of babies were born with serious birth malformations, such as brain damage and undeveloped limbs. Then, two doctors, Wittekind Lenz from Germany and William McBride from Australia, noticed that the babies' mothers had taken this new medicine for morning sickness. In 1961, Lenz proved the relationship between thalidomide and birth malformations. Then, the drug was taken off the shelves. But, by that time, thousands of babies had been born with these malformations, and nearly 40% of them had died. The rules for drug testing were not so strict back then, and in this case, it cost thousands of lives. Even though they had discovered thalidomide was a problem, scientists still didn't know why. It turns out that the answer lies in its chemistry, or more specifically, in its geometry. What researchers didn't know back then was that there were actually two versions of the thalidomide molecule. Thalidomide is made up of 3 connected rings of carbon and nitrogen atoms, 4 oxygen atoms, and a few more hydrogen atoms. It is a chiral molecule. Chiral comes from the Greek, hand or claw. The different versions of chiral molecules called enantiomers are made up of the same parts, but arranged differently. Just like your hands. They are like mirror images. Both hands have the same 5 fingers, but they are not identical. And molecules like thalidomide are the same shape. A chiral molecule has an atom, usually carbon, with 4 different groups attached to it. It is called the chiral center. A group can be from a single atom to a long chain. In some cases, 2 groups can even be connected. These groups are like your fingers. In each enantiomer, the groups are attached to the chiral center in the opposite order, so they are mirror images of each other. In thalidomide, for example, the chiral center is a carbon atom attached to one of the rings. It is bonded to 2 other carbons, a nitrogen and a hydrogen. In other words, the 2 enantiomers are mirror images of each other. Different receptors and enzymes within your body react with molecules in very specific ways. The fact that enantiomers are mirror images means that they can react to these receptors quite differently. In the case of thalidomide, scientists found that the R enantiomer helped with morning sickness, but the S enantiomer caused these serious birth malformations. After the researchers found that only the S version of thalidomide caused birth defects, they thought about isolating the R enantiomer, so they could continue to use it to treat morning sickness. But it turns out that the R enantiomer of thalidomide can actually switch to the S version while it's inside the human body. Which means that even if they had isolated 100% pure thalidomide R, it would still not be safe for pregnant women. But in 1998, thalidomide was approved. Almost 40 years after her rejection because of birth defects. This time, however, it was approved for the treatment of leprosy. Recent research is also leading some scientists to believe, in certain cases, thalidomide can help with a number of illnesses, including some forms of breast cancer. They just claim not to prescribe to any pregnant woman. Studies of this type are carried out by scientists in public universities. For example, there is a research group from Brazil that works on a part of drug development. This is the group of teacher Claudia Honorio. The group, supervised by Professor Claudia, is located at the School of Arts, Sciences, and Humanities of the University of São Paulo, and is called the Artificial Intelligence Group. They study the information contained in the DNA that give rise to proteins which determine interactions with possible drug candidates. Also, they suggest new chemical substances with bioactivity based on its chemical composition. The group uses chemoinformatics to carry out the research. Chemoinformatics is an interdisciplinary science that uses computer and information science resources to solve chemistry problems. Through a software, these researchers analyze several structures that can possibly act on some disease or some specific symptom, as well define their limits of toxicity, side effects, and contraindications. Imagine how important these studies are so new drugs can be manufactured and used to control many diseases that plague the population. So, guys, this is one reason why chemistry is so important for society, and also the deep study in the development of new drugs. We really appreciate your participation. That's all, folks. See ya.